Hi students, let us try to solve thermodynamics problems of GATE 2022. It is given for a system, single component system at a vapor liquid equilibrium, the variables like Helmholtz free energy, volume, entropy, and is denoting moles, okay, respectively. Okay, if the subscripts V and L denote vapor and liquid phase respectively. And if this is the system, you have to find out of the relationship were given which one are true and which one are false. So to solve this particular problem, you need to have some idea about the different equations that comes. Okay, let us discuss about the different equations that comes as a part. The set of equations to remember, you can see the enthalpy, Helmholtz free energy, Gibbs energy, and the differential equations relating these properties. Example, enthalpy for a closed system. Let us talk about the closed system, simple systems. And that means closed system means a container consisting of a component. Okay, that's considered as a closed system. There is nothing mass is going into the system, no mass is coming out of the system. This kind of systems you talk about the closed systems. Okay, in this substance containing in the closed system, these equations are valid. The enthalpy is equal to U plus PV. P is the pressure, V is the volume. The Helmholtz energy is U minus Ts. The Gibbs energy is U plus PV minus Ts is nothing but H minus Ts. And the differential equations relating entropy, enthalpy, and volume, pressures are given as follows. du is equal to Tds minus P into Tv. dH is equal to Tds plus V into dP. dA is minus SDT minus PdV. dG is equal to minus SDT plus VdP. These are the standard equations for us to remember. Okay, make sure you have to somehow remember the expressions. So based on these expressions, we are about to find out as per the given questions which options are correct and which options are incorrect. And these sets are Maxwell equation sets. So if you can able to remember these equations, you can able to solve the problem. And these equations which were written here are valid for the open systems like du, dh, da, dg. That means change in internal energy, change in enthalpy, change in Helmholtz free energy, and change in Gibbs energy. All these energies, all these expressions comes under the Maxwell's equations for applicable for the closed system. But in our expression, it is given that there is a vapor and liquid that are equilibrium. That means at the same time, at same temperature and pressure, both vapor and liquid exist at equilibrium. But in such cases, you can see the liquid molecules can go up to the vapor phase, and vapor molecules comes to the liquid phase. In such cases, if you can able to consider this as an open system where molecule exchange can take place, so you have to slightly modify the equations to do the necessary appropriate equations. Okay, let us do for open system. The small change we can introduce, because the things in the question it's asked mainly about the Helmholtz free energy. Then let us take this equation, modify for the open system. Okay, if Helmholtz free energy, earlier it is a temperature of dt and dV. That means Helmholtz free energy mainly it's a function of temperature and volume for the closed system. If it is an open system, the additional term will come which is denotes the chemical potential. That means if there are different molecules, different moles of different molecules are in the vapor and liquid, in such cases, along with this Helmholtz free energy, which is a function of volume and temperature, now additional expression comes mu I dni. I is denoting molecules of ith component which is there in vapor and a liquid. Okay, because in the in this question it is given there is only one molecule and one component present which is exchanging between these two phases, then I equal to 1 it is takes about. Okay, the simple is one molecule is present, one kind of molecule is present. The expressions for dA will convert to dA equal to minus PdV minus SdT plus mu and dN. N is representing the number of moles of component in a particular phase. So this particular equation applies to both, because vapor and liquid both are at equilibrium. So the expression can be, applies to both vapor and a liquid. So let us apply this equation 1 and for a vapor and liquid phase. Let us say I have taken some notations, that I have given notation V is for the vapor and L is the liquid. Let us apply that dV for dA for the vapor is nothing but minus PdV minus SdT plus mu into dN for a vapor phase, and dA for the liquid phase is equal to minus PdV in minus SdT plus mu IdA in a liquid phase. So at using these expressions for vapor and a liquid, then let us explore the option 1, which is given correct or incorrect. Okay, it is given dou A by dou V for a liquid phase at a constant temperature and constant moles of a liquid will be equal to dou A by dou V in a vapor phase at a constant temperature and constant moles in the vapor phase. That means these, according to the option 1, these two expressions should be the same when evaluated. Okay, let us evaluate different. Let us take this expression at the beginning and let us take this expression at the later, and let us see whether these both expressions gives the same value or not. And it is given that at same temperature at same liquid moles. Here it is given at a same temperature and same vapor moles. That means wherever outside this bracket, that means these, because we are evaluating this particular expression at constant temperature and constant number of moles for the left hand side, and evaluating this particular expression at constant temperature and constant moles in the vapor phase. So let us take the expressions. Okay, because it is said that temperature is constant, that means change of temperature dt equal to 0. Number of moles of liquid is equal to constant for this expression, that means dNL equal to 0. So apply these two conditions for the expression to get dou A by dou E. I know dA is equal to minus PdV minus SdT, which comes from here, plus mu I into mu into dN, because dNL, because we are evaluating for the liquid phase, dNL equal to 0. That means this expression is 0 because dN equal to 0 for the liquid phase, and dt is the temperature equal to 0. The only thing that remained is these two expressions. So dA by dV at constant temperature and constant liquid moles is equal to minus P, because there is only one derivative which is evaluated at constant temperature and constant number of moles. That dA by dV can be written as dou A by dou V. That means partial derivative of A with respect to volume at constant temperature T and constant moles of the liquid, which is equal to P. Let us evaluate this right hand side expression. Similarly, dA for a vapor phase equal to minus PdV minus SdT plus mu into dN for the vapor phase. So similarly, for the vapor phase on the right hand side expression, it is evaluated at constant temperature and constant number of moles. So for case temperature equal to constant, dt equal to 0, moles of vapor. Okay, this is the vapor, this is the vapor phase. Okay, this is the vapor phase. dNV is equal to 0. Okay, and now and only these two expressions remained. You take this particular expression to the bottom, dA by dV at constant volume, vapor phase at temperature T and number of moles of the vapor phase is equal to minus P. You can observe both expression led to the same value, which is called minus P. That means the option 1 is the correct option. Okay, let us similar way, let us go for the option number 2, 3 and 4. The option number 2, 3 and 4, it signifies that dou A by dou N at for the liquid phase at constant temperature and constant volume of a liquid, which is equal to dou A by dou N for the vapor phase at constant temperature T and volume of the vapor phase. Earlier it was the moles, you can see now it is the volume. Okay, let us evaluate. Same expression is valid. So let us take this left hand side expression to evaluate first. dA for the liquid phase is equal to minus PdV minus SdT plus mu into dN for the liquid phase. And it is given temperature is constant and volume of the liquid is constant. So T equal to constant is dt equal to 0. Volume of the liquid constant is nothing but dV L equal to 0. If you put these two zeros, the remaining expression is dA by dN for the liquid phase at constant temperature T, and volume of the liquid is mu, chemical potential of the liquid phase. Okay, and you can see that because the derivative of A with respect to N evaluated at a constant temperature and constant volume, dA by dN will become partial derivative A with respect to partial derivative of N. It's okay, and that means I got the value of mu L. Similarly, if you can able to do for the vapor phase, you can see dA by dN for the vapor phase at constant temperature T and volume will give rise to chemical potential for the vapor phase. Okay. Here for the first expression you get chemical potential for the of liquid. For the second expression you get a chemical potential for the vapor. Okay, then what is this chemical potential of L and chemical potential of E? You can see that as in the question it is given, vapor and liquid both are at same conditions. That means both are at equilibrium. If both vapor and liquid are at equilibrium in the absence of any change, then chemical potential, that means true driving force in the vapor, should be equal to true driving force for the liquid. So if you apply this chemical potential equality, then mu L will be equal to mu V. Therefore, these two expressions is giving, that is mu vapor equal to mu liquid. That means both expressions are giving the same answer. That means the option 2 is correct. Let us go to the option number 3. Option number 3 says that A plus PV by N for the liquid phase is equal to A plus PV by N in the vapor phase. That means they are equating some property of a liquid will be equal to some property of vapor, and let us see what is this property they are trying to relate. A plus PV, let us figure out what is, I know what is A and what is pressure into volume, and can I get a relationship what is A plus PV and A plus PV for the vapor and A plus PV for the liquid. Okay, then let us using some expressions in this example, they are comparing a property in the vapor and the liquid in this option. So bring the terms only to the single variable. I know A equal to U minus Ts, which is therefore A plus PV is equal to U minus Ts plus PV. Therefore A plus PV is equal to U plus PV minus Ts. So U plus PV is nothing but H minus Ts, which equal to G. That means the A plus PV is nothing but Gibbs energy. G by N means Gibbs energy by moles, that is molar Gibbs energy for the liquid phase. Similarly, if you do it for the vapor phase, you get Gibbs energy with respect to the moles. That means molar Gibbs energy, total energy divided by moles will give you molar Gibbs energy for the vapor phase. And similarly, the chemical potential, which will be the same for the liquid and a vapor, and this chemical potential nothing but it has come from the Gibbs energy in general. Okay, don't worry, if both vapor and liquid are equilibrium, that means Gibbs energy, molar Gibbs energy of the liquid should be equal to the molar Gibbs energy of the vapor. That means these both expressions give the same answer. That means option 3 is also correct answer. Let us explore the option number 4, which is the last option, and it is said that A plus Ts by N for the liquid phase is equal to A plus Ts by N for the vapor phase. Let us get both with respect to only single variable now. So A equal to U minus Ts. So A plus Ts means U minus Ts plus Ts, okay, which is equal to U. That means A plus Ts is nothing but internal energy. That means I can replace A plus Ts with internal energy. So U by N is a molar, that U is in energy units and N is the total moles. U by N will become molar internal energy of the liquid phase. This is the molar internal energy of the vapor phase. And you can see both are, because in general liquid molar energy is less compared to the, internal energy of the liquid is less compared to the internal energy of the vapor. That means molar internal energy of the vapor, because vapor has got higher energy, with respect to the molecules, and this molar internal energy of the liquid is less compared to the vapor. That means both expression cannot be the same. So that is why option 4 is incorrect. Among the options given 1, 2, 3, 4, 1, 2, 3 are correct. The fourth one is incorrect. Let us go to the next problem. Let us go for the question number 29. It is said that 5 moles of benzene, 8 moles of toluene and 7 moles of xylene are mixed at a 25 degrees centigrade and 1 bar. Assuming the formation of ideal solution and using the universal gas constant value, we have to find out what is change in entropy because of this mixing. See, let us take for example, that is a standard enthalpy of mixing we can calculate. Later on, I can explain you how this equation has come. So, if there is a container consisting of pure benzene, example, pure toluene and pure xylene. All the three are mixed in a container. So, after the SBIG, that means entropy of pure benzene. This STIG means entropy of pure toluene, and SXIG is entropy of pure xylene. IG is representing that all the gases are behaving ideally. Okay. So, after mixing, what is the fraction of benzene? Okay, in this container is YB, fraction of toluene is YT, fraction of xylene is YX. Okay, and after SIG is representing the entropy of the mixture after mixing. So, entropy of the mixture after mixing the three components can be calculated using SIG. That means total entropy of the three components in the container is YB into SBIG, YT into STIG, YX into XXIG minus R into sigma I equal to 1 to 3 XI into ln X. This is a standard formula you can able to refer, and fractions XI is representing the fraction of the molecules. You can, don't worry, you can replace XI with YI also. So finally you can observe the third term. This shows, that means the contribution of pure benzene is YB into SBIG, the contribution of pure toluene YT into STIG, the contribution of pure xylene in this mixture is YX into SXIG. But they won't remain at single location. They'll mix with each other. Once the benzene is mixed with toluene, xylene, all the three components mix in the container. Because of this mixing, the additional entropy that comes in place, that additional entropy because of this mixing is minus R equal to I equal to 1 to 3, because three components, Xi into ln X or Yi into ln Yi. So because it is given, you are supposed to calculate entropy change, because this is the change in entropy. That means minus R equal to 1 to 3 Xi ln Xi is equal to minus R into Yb ln Yb plus Yt ln Yt plus Yx ln Yx. So you going to find all these because it is given. Okay, R, the minus R, that means a universal gas constant value is given. You are supposed to calculate Yb, Yt, Yx. So to calculate Yb, Yt, Yx, the moles information is given. Total number of moles is benzene is 5, toluene is 8, xylene is 7. So the fraction of benzene in this mixture is moles of benzene by total moles, which is benzene plus toluene plus xylene. Similarly, you can able to calculate the fraction of toluene in this mixture and fraction of xylene in the mixture. So after plugging all the numbers in this equation, I get Yb equal to 0.25, Yt equal to 0.4, Yx is equal to 0.35, R equal to 8.314 joule per mole Kelvin. So entropy of mixing you are supposed to calculate. If you plug in all the numbers in this equations, you get the total entropy of mixing is 8.983 joule per Kelvin per mole. You can have to worry about the unit system now. So you can see the R has the units of joule per mole Kelvin. So finally the entropy of mixing, you get the value of 8.98 joule per mole per Kelvin. So what it is asked, the total entropy change in joule per Kelvin. That means you are somehow you have to eliminate this denominator, because they don't want molar entropy of mixing, they want total entropy of mixing. Okay, if that is the case, you have to somehow multiply this with the total moles in this particular mixture. Okay, total moles in this particular mixture, you can talk about the entropy of mixing into total moles, that means total moles of benzene, total moles of toluene, and total moles of xylene, that is 5 plus 8 plus 7. If you can plug in these numbers and multiply these two expressions, you get the entropy of mixing is 179.61 joule per Kelvin. Okay, that is what the answer you are supposed to write. Other many of the students, they stop at this number, but please worry that whether they have asked molar entropy or the entropy of or total entropy. So how this expression has come, I will give a brief introduction. So I have explained this in the GATE 2025 thermodynamics problems. You can see that if there is a pure A molecules, because I am explaining using binary mixture so that you easily understand. Suppose imagine a container containing of A and B molecules. So the A and B are mixed. So before mixing, the pure A has got the entropy of SAIG, pure B entropy of SBIG. Okay, after mixing, the total entropy of this mixture is SIG. Okay, the fraction of A in this mixture is YA, the fraction of B in this mixture is YB. The contribution of A, pure A, contribution of entropy of pure A in this mixture is S bar AIG. The contribution of pure B in this mixture is S bar BIG, because once it comes in the mixture, the property will change. It is no more is SAIG, it will become S bar AIG. Here it will become S bar BIG. S bar AIG and S bar BIG is representing the contribution of pure A in this mixture, and this is contribution of pure B in the mixture. Here it's a pure only A, it's a pure only B. These are the notations you are supposed to learn in thermodynamics. And there is a summability relationship. That means the total entropy is a combination of individual entropies, that is sigma yi into S bar ig. Because it's a binary mixture, the total entropy of this mixture is nothing but ya into S bar ig plus yb into S bar big. I know there is expressions for S bar AIG and S bar BIG. S bar AIG is nothing but SAIG, that means pure entropy of A, minus R ln by A. ln y is a fraction of A in the mixture. So if you know these two informations, you can able to calculate the S bar AIG. And if you want to calculate S bar BIG, this is the equation. S bar BIG is equal to SBIG minus R ln by A. So simply 2 and 3, put the equations in 1. So you get total entropy is nothing but Ya into S bar AIG, SAIG plus YB into SBIG minus R Ya ln Ya minus R Y, A YB ln YB. Okay, this is R into YB ln YB. So therefore, if you put this in sigma relationship, you get R into sigma yi ln yi. This is the entropy of mixing term. The contribution of pure A, the contribution of pure B, and the third term, which because of the mixing of A and B, this additional entropy that comes, this is called entropy of mixing, which can be calculated using this formula minus R sigma yi ln yi. This is how the expression has come to solve this particular question. Let us move to the next question. Okay, let us deal with the question number 37. It is given n moles of ideal gas undergo two-step process as shown in the figure. Okay, that means, and the system has undergone two steps. That means it is initially at the state 1, it brought it to the state 2, which is it brought it to state A. From A, it brought it to the state 2. That means it has gone from state 1 to state A to state 2. Okay, and this is what the it is given. P, V and T denotes pressure, volume, temperature of the gas during this process. The gas initially at the state 1, that means here P1, V1, T1 are the state 1 variables, and from state 1 under an isochoric process to reach to state A. That means system has taken from the state 1 to state A through the process which is called isochoric process, which is represented by A. Okay, the path followed from state 1 to state A through isochoric process. From next is then undergo isobaric expansion to reach to state 2. That means from state A, it reached to the state 2, the state 2 consisting of variables P2, V2 and T2. The process here is called isobaric process. Why it is called isochoric process? Because during the system is taken from state 1 to state A, the volume is not changing. The volume is at a V1 only. So that is why constant volume process, it is called isochoric process. For the state 2, it is taken from state from A to 2. During this state A to state 2, the pressure is not changing. Pressure will remain at a P2. That is why it is called isobaric process. So at state 1, it is P1 and V1. At state A, it is P2 and V1. At state 2, it is called P2 and V2. Okay, at state 1, the temperature is T1. At state 2, the temperature is T2. At state A, it is not given. Let us assume there is a certain temperature which is called T at at state A. So what we are supposed to find out? For an ideal gas, Cp minus Cv is equal to Nr, whatever it may be, where Cp, Cp and Cv are the heat capacities at constant pressure and constant volume respectively, and assumed the temperature independent. The heat gained by the gas in the two-step process is given by, that means during this system has brought from state 1 to state 2 through state A, then we have to find out what is the heat involvement during this particular entire process. Okay, let us do that. That means you are supposed to find out Q, right? You have to take the help of thermodynamics first law, and state 1 variables are represented by P1, V1 and T1. State A, here it is represented as P2, V1 and T, and state the last one, okay, that is state 2. That means here it is called pressure P2, volume B2, temperature T2. Let us apply the first law for the first step, which is called isochoric process, and the second step it is called isobaric process. So then generally first law is delta is equal to Q plus W. Q will be the positive because W will be the positive. Both and Q and W will be the positive if you provide heat and work to the system. And Q and W will be negative if you heat, system has lost supplied heat to the surrounding. That means anything comes from the system, it is a negative process, and anything you are supplying to the system, whether it is a heat or work, it should be taken as a positive. That is what the sign convention you are supposed to be taken. So let us take the path 1 to A, that is path 1 to path A. Delta, that is and change in internal energy in the path A is nothing but heat involved in path A plus work involved in path A. Similarly, and for the path B, which is isobaric process from A to 2, the change in internal energy in the second path, which is nothing but heat involvement in the path B and work involvement in the path B. And what we are supposed to find out, heat gained by the gas in the two-step process. That means you are supposed to find out QA plus QB, because these is QA and QB are the heat that is involved in the both the process. That means total Q you have to find out is QA plus QB. What is QA plus QB? QA is equal to delta UA minus WA. QB is equal to delta UB minus WB. So what is QA plus QB is delta UA plus delta UB minus WA plus WB. Okay, and what is here, what kind of work? That means if you wanted to evaluate the works, what kind of work is involved? This is called displacement work. Work can be of many types. The work which is involved in this particular process is the displacement work. Displacement work can be evaluated using this equation minus integral PdV. And the second one, how you can able to get the change in internal energy, because it is said that in ideal gas, the change in internal energy of ideal gas by bringing the system from state 1 to state A or state A to state 2, this equation holds. That means integral Cv dt is the equation you are supposed to use if it is an ideal gas that is involved in the process. Okay, now you know work and delta U. Let us do that. What is the change in internal energy in the path A, which is isochoric process, is nothing but in Cv into integral what is the T1 to T, because it's in this particular isochoric process, it is the initial temperature is T1, final temperature here it is T. So you have to take the integral Cv dt. That means Cv is a constant, it's come out of the integral. So integral T1, I mean it's initial temperature T1 and final temperature is T. So delta UA is nothing but Cv into T minus T1. Similarly, delta UB. In the second path, which is isobaric process, again the same formula used, integral Cv dt. Cv is a constant, come out of the integral initial temperature to final temperature. In the second path, the initial temperature is T, final temperature is T2. So Cv into integral T to T2 dt. It is nothing but Cv into T2 minus T1. So how you calculate work? Okay, work in the process, first process, okay, isochoric process. Any displacement when calculated minus integral PdV. So integral V1 to V2. That means volume here is V1 and here it is volume also V1. You can see the volume is not changing in the isochoric process, which is a constant volume process. So in such cases dV equal to 0. So work, displacement work involved in this process is equal to 0. Similarly, let us calculate the work in the isobaric process. So work in the isobaric process means minus integral P dV. So into the limits, it's from V1 to V2. Okay, initial volume is V1, final volume is V2, the pressure into dV. Because isobaric process, the pressure is constant. So bring this pressure out of the integral. If you can able to bring this out of the integral, integral V1 to V2 dV is nothing but V2 minus V1. What is the pressure? Because pressure is constant, which is P2, P is replaced with P2. Okay, now we got all the expression. Let us plug in this particular equation to get the total heat involved in the process. Therefore, Q equal to QA plus QB, which is nothing but delta UA plus delta UB minus WA plus WB. Okay, let us calculate Cv into T minus T1 plus Cv into T2 minus T1 minus of WA plus WB. WA equal to 0, whereas WB is minus P2 into V2 minus V1. Substitute all and you get the final expressions. Total heat involved in both the process is P2 into V2 minus V1 plus Cv into T2 minus T1. Okay, this is what option you are supposed to pick. So let us move to the next problem. So let us deal with the question number 47. A substance at 4 degrees centigrade has a thermal expansion coefficient beta, that is 1 by V into dou V by dou T at constant pressure equal to 0, and isothermal compressibility KT is nothing but 1 by V into dou V by dou P at constant T is given. So the molar volume is given 18 into 10 power minus 6 meter cube per mole. If S is the entropy, then at 4 degrees centigrade, the quantity V into dou S by dou V at constant temperature should be calculated for this substance in joule per mole Kelvin. Okay, for this you have to, by looking at these expressions, you should get an idea that somehow you have to use the Maxwell's equations. Okay, the thing is, there is a certain substance at 4 degrees centigrade which the beta is 0. That means thermal expansion coefficient is 0. That means mostly the liquids have the beta equal to 0. And given the KT, that means isothermal compressibility value and molar volume is given. You are supposed to find out V into dou S by dou V at constant T, which is a question number. Given it is 0, and let us use the Maxwell. Before I go Maxwell equations, when you talk about any pure substance, okay, and the pressure, volume and temperature can be related. It's a general phenomenon. Degrees of freedom you can calculate. You get an idea of how many variables are required to specify a substance. And C minus P plus 2, C is a number of components, minus P is the total number of phases plus 2. Number of components, it's a substance is consist of one component. It is C equal to 1, phases are phases equal to 1 because a pure substance which is one phase, it's they talk about, and plus 2. Number of variables to be specified for this quantity of a liquid here is, for a pure substance, is 2 variables. So here something to do with volume, because you can see that they are dealing something to do with dou V by dou T, dou V by dou P, dou S by dou V. Something volume is involved in this particular calculations. So because 2 variables has to specify, if you want to calculate the volume, then it should be function of 2 variables, because degrees of freedom you have got it is 2. That means if you want to deal with the volume, which is something function of temperature and pressure. So if it is a volume is a function of temperature and pressure, total derivative you can written as dV equal to, with respect to dt, that means temperature of function of temperature and function of pressure. So dV equal to dou v dt into dP, and these are the partial derivatives, dou v by dou t at pressure, constant pressure, plus dou v by dou p at constant temperature. Okay, this is how you can able to write down the total derivative. It's a standard process. Okay, divide this equation by v, you get 1 by v into dou v by dou t at constant pressure into dt, and 1 by v into dou v by dou p at constant temperature dt. The first expression, it is called beta, which is called volume thermal expansion coefficient. Okay, that is what it is given here. And the second expression it is given is called minus k, isothermal compressibility. K is called isothermal compressibility. That particular value is also provided here. Okay, that means you are supposed to use this particular equation to evaluate this particular value. Okay, then if you do it at here, the volume is not changing here in the container. You are talking about the fixed to calculate the property in a fixed volume. So dV equal to 0 in this expression. The dV equal to 0, that means dV by V equal to 0. If you put dV by V equal to 0 and you calculate dP by dt at constant volume, is nothing but beta by k. Because there is only you are evaluating at a constant volume, the dP by dt will become dou P by dou T. So dou P by dou T at a constant volume is nothing but beta by k, which is equal to 0, because the value of the beta is given 0. So dou P by dou T at V equal to 0. Okay, and you have to get the Maxwell relations. The Maxwell relation, one of the Maxwell relationships is found that dou S by dou V at constant temperature T equal to dou P by dou T at constant volume V. That means if you know dou P by dou T at constant volume, which will be the value of this particular expression will be equal to dou S by dou V at constant temperature. This is what the Maxwell relationships. You already found that the value of dou P by dou T is equal to 0. So what happens, the value it is 0, the value of dou S by dou V at constant temperature is also equal to 0. That means V into dou S by dou V at constant temperature is nothing but 18 into 10 power minus 6 into 0, which is 0. That means the answer here is 0. That means the thing is, you always have to remember the Maxwell relationships, which is part of integral part of the very fundamental thermodynamics relationships. And one thing is how to formulate this equation using the concept of degrees of freedom and the expression that connects the thermal expansion coefficient and isothermal compressibility using this particular formulations. It's a very easy, and only thing is you have to practice well, because majority of the times you are going to you will get asked based on this kind of formulations. Thank you. Let us go to the next problem. Let us deal with the question number 48. It is given molar excess Gibbs free energy GE. The excess free energy of a liquid mixture of A and B is given by the particular expression. And that means there is a container consisting of the molecules A and B, and excess energy of this particular molecules containing the A and B is given by these expressions. GE by RT is equal to XA into XB plus C1 plus C2 into XA minus XB, where XA, XB of the mole fraction of A and B respectively. Universal gas constant value is given, temperature is in Kelvin, C1, C2, temperature dependent parameters. That means at 300 Kelvin, C1 value is given and C2 value is given. What you are supposed to find out is integral 0 to 1 ln gamma A by gamma B into dxa. So to get this expression, you have to somehow found the relationship in which is the expression which is given and the thing which are supposed to calculate. There is a relationship between the, there are equations connecting using Gibbs-Duhem equations, and there is a relationship between the excess Gibbs energy and the activity coefficients. Gamma and gamma B is denoting the activity coefficients. So there is a relationship. This is d by dx1 into GE by RT is nothing but ln gamma 1 by gamma 2. This is the standard expression that connects the excess Gibbs energy with respect to the activity coefficients. So it is given with respect to 1. If you can change it, because here you take the x1 as dxa in this exam and in this question, then d by dxa of GE by RT is nothing but ln gamma A and gamma B. 1 and 2 components are nothing but A and B components. So what is, let us go ahead. What we are supposed to calculate? Integral 0 to 1. You are supposed to calculate this particular value. Let us integrate this expression. Integral of d by dxa of Ge by RT into dxa is nothing but integral 0 to 1 ln gamma A by gamma B into dxa. And you can see a derivative and integral. These both will get cancels out. Finally, the integral of 0 to 1 of this particular is next expression is nothing but Ge by RT from 0 to 1 is nothing but integral 0 to 1 ln gamma A by gamma B. That means the one which is given the expression is the value which is nothing but the integral 0 to 1 gamma A by ln gamma A by gamma B into dxa. So that means if you can able to calculate Z by RT between the limits 0 and 1, that means you have already calculated this particular value. That means G by RT which is given XA into XB into C1 plus C2 into XA minus XB between the limits 0 to 1. Let us substitute these limits in this equation and get the value. And if you what is the expression you are supposed to put in? When XA equal to 1 to XA equal to 0. What is XA equal to 1? Then wherever you see the XA, you are supposed to put the value of 1. Wherever you see the XB, you are supposed to get the value of 0. Because when XA equal to 1, XB equal to 0. That means if you put the limits XA equal to 1 here, then this entire expression will be equal to 0 because XB equal to 0 here. When you put XA equal to 0, at that time XB equal to 1 because XA plus XB equal to 1. That means if you put the limit 0, that means XA equal to 0, in that wherever the XA equal to 0, the XB value will be equal to 1. That means the entire, that means if you get the integral 1 into 0 plus C1 plus C2 into 1 minus 0, then minus 0 into 1 plus C1 into C2 into 0 minus 1. Then you can see it is every expression is multiplied by 0. That means the entire value of ZA by RT is 0. The answer we can expect is Z by RT is 0. When Z by RT is 0, 0 to 1 ln gamma A by gamma B into dx is also equal to 0. So this is how we can able to solve this particular question. Thank you. Let us move to the next question. Question number 49. For a pure substance, the following data at saturation conditions are given: ln Psat value and temperature value. That means for a pure substance at two different temperatures, the value of ln saturated pressures are given. Assume vapor phase behaves ideally. The molar volume of the liquid is negligible and the latent heat of vaporization is constant over the temperature range. The universal gas constant value is given from the above data, and the estimated latent heat of vaporization at 360 Kelvin we are supposed to find out. Okay, and if that is the case, and let us use 360, it is 360 is given. Finally, let us calculate. So vapor and liquid phase values, let us, because it's a pure substance, is at a saturated condition. That means at a saturated condition, there is a high possibility vapor and liquid both exist at equilibrium. So what we are supposed to find out is what is the latent heat of vaporization during this particular conditions. And the equation, the Clapeyron equation, that is a standard equation to find out how the saturation pressures are changes with respect to temperature, or how the temperature is changing with respect to saturation pressures. That means it is talking about the vapor and liquid equilibrium, the temperatures and pressures to have the both and vapor liquid connected by the equation, which is ln P2 by P1 is equal to delta H by R into 1 by T1 minus 1 by 2. And you can see the temperature here are given at 350 and 370, but here it is asked that latent heat of vaporization at 360. And you should also, there is one more information is given: latent heat of vaporization is constant over a temperature range. That means over the temperature range of 350 and 370, the latent heat of vaporization is not changing. Okay, that is what the first question, first takeaway. So let us use this equation P2 and P1, T1 and T2. So these informations of P2 and P1 is given in terms of ln Psat, and temperature is given in terms of 350 and 370. So ln P2 sat is equal to 1.386. So P2 saturated is nothing but 3.998 bar, which is nothing but 3.998 into 10 power 5 Pascal. Because you have to convert in everything Pascal, because universal gas constant is given in terms of joule per mole Kelvin. So you are supposed to use only SI units. The pressure in the SI unit is Pascal. So keep that in the same terms. ln P1 sat is equal to 0.693. Where P1 sat is equal to 1.993 bar. So these are the P1, P2 values for me. Okay. So therefore P1 saturated is equal to 1.999 into 10 power 5 Pascal. Temperature T2 is nothing but 370 Kelvin. T1 is nothing but 350 Kelvin. That if I have the informations of P1 and P2 and T1 and T2. Let us use the Clausius-Clapeyron equation to find out delta H of vaporization. Okay, the delta H of vaporization. So if you keep the delta H of vaporization on one side, rest everything on the another side, you get R into ln P2 by P1 by 1 by T1 minus 1 by T2. If you substitute the values of pressures and temperatures and universal gas constant values, you get the equation 37308.95 joule per mole. That means 37.308 kilojoule per mole. So this is the answer you are supposed to give. That is what enthalpy of, latent heat of vaporization. And thank you.